Okay, so this is part 3, and I think I last left off with you answering question number 9 on your own, so you can go ahead and do that. Question number 9 on your own from the book, you're basically filling in the formula for density, which you can, of course, find right here, formula for density. So the next thing we'll do is using density to identify substances. Okay. So let's see what the next question is. Let's go to number 10. What are 2 reasons why density is a useful property for identifying substances? All right, so this is why we're going to read this part right here. And 2 reasons. Haha. Look at that. Questions, answers right here. So let's read. All right, using density to identify substances. Density is a useful property for identifying substances for 2 reasons. First, the density of a particular substance is always the same at a given pressure and temperature. That's reason number 1. For example, the helium in a huge airship has a density of 0.000163 or 663 grams per cubic centimeter at 20 degrees Celsius and normal 20 degrees Celsius in normal atmospheric pressure. You can calculate the density of any other sample of helium at the same temperature and pressure, even the helium in a small balloon, and you will get the same decimal grams per cubic centimeter. Second reason, the density of one substance is usually different from that of another substance. Check out the table below to see how density varies among substances. So you have these substances, tells you the density, another set of substances, and tells you the density. But with these 2 questions, or these 2 right here, we have the 2 reasons why density is good to use to identify. So let's go back and take a look. Remember, the first one is, first, the density of a particular substance is always the same at a given pressure and temperature. Let's put that in. Shorten it. Density is always the same at a given temperature and pressure is the first reason. You can actually put number 1 right here. 1. 1. There you go. And then reason number 2 was, come on in. Okay, I'm not sure where I left off here, guys. It's been a kind of weird last hour or so here on campus at Commonwealth, but let's go ahead, and I think I was answering number 2, and perhaps if I hit backwards on my screen, I would know. Ha! We did this. Okay, so I was in the middle of answering part 2, so here we go. And, well, I'm just going to type the number 2 part here. So we were looking at what was the second reason why density is good to use to describe matter. And first one, density is always the same at any given temperature and pressure. And I think the other answer would be something along the lines of, if I can find it again, something along the lines of, I remember, of secondly, the density of one substance is usually different from that of another substance. That's what we're going to put in. So part 2 would be, the density of one substance is usually different than that of another substance. That's what I'm going to put in here for part 2 of this. I'm going to make it even shorter by saying densities are usually different. Densities of substances are usually different from each other. Okay, so that will be the answer for number 10. Okay, pause that, write it down if you need to, and because it's about to go bye-bye, so we can move on. All right, so now I have, there we go. Answering for question number 11. Using table 45, list the elements mercury, water, gold, and oxygen from the densest to the least dense. Okay, so let's look at our table. Here we go. So we have, there's water, there's mercury, copper, gold, from dense to least dense. So it should be from densest to least dense. So which one is going to be the most dense? Because basically it's going to be the one with the bigger decimal number out of those. Mercury's at, well, I think it's gold. Gold is the most dense. See that? Then mercury, lead, silver, copper. Then zinc, iron, pyrite, water, oxygen, then helium. Okay, so gold is the most dense. So the order should be gold, right? And then is it going to be mercury or oxygen? I think it would then would be mercury. Mercury, oxygen, or water. What's next? Let's take a look. Oxygen, water, water, and then oxygen. So then it will be water, and then oxygen. Okay, so hopefully you got those down, and that was the answer for number 11. Writing down from the most dense to the least dense. That order again, just in case you didn't see the words: gold, mercury, oxygen, and then water, then oxygen. Number 12. What will happen if you shake the jar in Figure 12? So what will happen if you shake the jar in Figure 12? That's a density column that we're doing in class, which is right here. So let's read about that a little bit, just in case you didn't know that this is the experiment that I was trying to do in class. Liquid layers. What do you think causes a liquid in Figure 12 to look like the way it does? Is it magic? Is it trick photography? Nope. It's difference in density. There are actually 4 different liquids in a jar. In my class, we did 5 different liquids. Each liquid has a different density. Because of these differences in densities, the liquids do not mix together, but instead separate into layers, with the densest layer on the bottom and the least dense layer on the top. The order in which the layers separate helps you determine how the densities of the liquids compare with one another. The density challenge. Imagine that you could put a lid on the jar in the picture and shake the liquids. Would the different liquids mix together so that the 4 colors would blend to one or interesting color? Maybe for a minute or two, but if the liquids are not soluble in one another, they would start to separate, and eventually you'd end up with the same 4 layers. So basically this is saying you can tip it, shake it a little bit, and if they're not soluble, which means they're unable to mix with each other, okay, then eventually the layers will start to separate again. Okay, so with these 4 liquids, completely they would separate. The 5th liquid that I use in my class is alcohol, and sometimes the alcohol is soluble with the layer that's underneath it, which should be the oil, and sometimes that won't separate as well, and so it looks like a little bit of murky on top if you happen to shake yours up, and that's because I use a 5th layer with the alcohol, creating another layer that's a little bit soluble, which means it can mix with something, so it's not as dense as the other layers. Okay, so now we can actually go ahead and answer this question. What will happen if you shake the jar? Oh yeah, so I think the easiest thing would be they would mix. It would be like this. Here's number 12. They would start to separate, and eventually you'd end up with the same 4 layers. Let's write that as our answer. There you go. They would start to separate and eventually end up in the same 4 layers. Okay. Question number 13. Is 40 milliliters of oil denser than 25 millimeters of vinegar? I wonder where that came from. Let's find out. So, oil and vinegar. I bet you that's what we're talking about next. Question and answer number 13 is right around in here. The same thing happens when you mix oil and vinegar to make salad dressing. When the layers separate, the oil is on top. But what do you think would happen if you added more oil? What if you added so much oil that there was several times as much oil as there was vinegar? Surely the oil would get so heavy that it would sink below the vinegar, right? Wrong. No matter how much oil you have, it will always be less dense than the vinegar. So it will always rise to the top. The same is true for all the 4 liquids shown in figure 12. Even if you add more yellow liquid than all the other liquids combined, all of the yellow liquid rise to the top. That's because density does not depend on how much of a substance you have. So it looks like question 13 and 14 are answered right in here. So let's go back and take a look with 13 and 14. Is 40 milliliters of oil denser than 25 millimeters of vinegar? So it's 40 milliliters of oil. So basically, will the oil sink in the vinegar? Guess what your answer is going to be? Nope. The oil will always stay on top. Number 14, density is dependent on the amount of substance you have. True or false? False. It does not matter the amount of substance you have. Okay? So let's move on to, there's a review. We'll go to chemical properties. So now we're going to find an answer to number 15, which should start here, chemical properties. And as you can see, all of this will help you answer number 15. Chemical properties. Physical properties are not the only properties that describe matter. Chemical properties describe a substance based on its ability to change into a new substance with different properties. Chemical properties describe a substance based on its ability to change into a new substance with different properties. Okay, I think we're answering part of number 15. Which of the following are true about chemical properties? They indicate a substance's ability to change identity. Yeah. They indicate one substance's ability to react with another. They describe matter, or they can be observed with your senses. Well, let me go back to the reading, because as you can see, all of this says 15. So I'll just finish reading first. Going back with chemical properties. Chemical properties describe a substance based on its ability to change into a new substance with different properties. Ding! We saw that one. For example, a piece of wood can be burned to create a new substance, ash and smoke, with properties different from the original piece of wood. Wood has the chemical property of flammability, the ability to burn. A substance that does not burn, such as gold, has a chemical property of non-flammability. Other common chemical properties include reactivity with oxygen, reactivity with acid, and reactivity with water. The word reactivity just means that when two substances get together, something's going to happen. Oh yeah. Observing chemical properties. Chemical properties can be observed with your senses. However, chemical properties aren't as easy to observe as physical properties. For example, you can observe the flammability of wood only while the wood is burning. Likewise, you can observe the non-flammability of gold only when you try to burn it and it won't burn. But a substance always has its chemical properties. A piece of wood is flammable even when it's not burning. Okay? So with this, we can answer our next question. Which of the following are true of chemical properties? They indicate a substance's ability to change identity. Yes. They indicate one substance's ability to react with another. Well, yes, it does. Do chemical properties describe matter? You know it. And D, they can be observed with your sensors. Well, yes, all of these are true about chemical properties. And number 16 and figure 13 on page 47. Why isn't there rust in the painted areas of the car? Oh, I remember this question. Let me go back and take a look at that old beat-up car. Here. Some chemical properties of car maintenance. So, reading this. Look at the old car in figure 13, I think, or 15. Its owner calls it Rust Bucket. The name of the car is Rust Bucket. That's funny. Okay. Why has this car rusted so badly while some other cars the same age remain in great shape? Knowing about chemical properties can help you answer this question. Okay. Most car bodies are made from steel, which is mostly iron. Iron has many desirable physical properties, including strength, malleability, and a high melting point. Iron also has many desirable chemical properties, including non-reactivity with oil and gasoline. All in all, steel is a good material to use for car bodies. It's not perfect, however, as you can probably tell from the car shown here. And if you look at here, paint doesn't react with oxygen. Ding! So it provides a barrier between oxygen and the iron in the steel. Question number 16. In figure 13 on page 47, why isn't there rust in the painted areas of the car? Paint does not react with oxygen. That's what you want to type there. And this video is about to run out of time, so I'll just tell you that's what's going on over here. Number 16, please make sure you have that information here. for answer 16.